Hi everyone, I'm Jess. Just a quick show of hands because I know a lot of you guys took Calc 1000. So can I see a show of hands? How many of you guys took Calc 1000 last semester? Oh wow, majority of people. Okay, awesome. Keep your hand up if you came to one of my prep sessions at the end of the semester or throughout the semester. Okay, so about half of you guys. So some of you guys know me. That's great. So again, my name is Jess. I went to Western myself. I bleed purple. I love Western. I was a TA at Western, but unfortunately, I did not TA this course. But I did tutor some students in this course before, and I have to say, this year the course seems to have changed a little bit, especially with these weekly tutorials and lectures and whatnot. So today, I'm going to cover these topics as much as I can. And I can bet you, I talked to a bunch of students, I bet you that most of you guys are here probably for recursion, applications of differential equations, and probably some linear differential equations, right? I'm going to go through all of these because I want to make sure I'm catching you guys up. The first weekly tutorial and probably the second one are a little bit more intense just because I have kind of 2 weeks, 3 weeks that I need to catch you guys up on. And then as Robbie said, the weekly tutorials are more focused on making sure you guys understand what's happening so you can do these quizzes that I think you guys have to do them by Tuesday, something like that. But I'm going to get you guys prepared for those and so that you are more prepared leading up to your midterm test, right? So please write down my email. I know there are topics here that some of you guys have learned already. For example, there's Bernoulli equation, there's separable differential equations, there's equilibrium, stability. I'm going to cover that next week, just because even with this list, I probably won't be able to cover everything, but I'll do my best, okay? So if you have questions pertaining to any of the topics that I'm talking about, please type them in the Q&A and I will get to those. But if you have any private questions for any topic that's not on this list, feel free to email me. I'll get back to you there. Let's dive in, everyone. So you should have received a booklet. Okay, so a booklet, and the booklet pretty much covers everything from today. So it breaks down into, first, we're going to go through the basics of mathematical modeling. There's probably 1 or 2 questions they can ask on the test or on the midterm type thing. Then we'll talk about allometric versus isometric relations, recursion, a big part, and then your differential stuff, including the application of word problems, okay? So let's dive in. The first thing you guys talked about in class this semester is mathematical modeling. That's just a really fancy way of saying, hey, we want to describe the real world, okay? The real world, a lot of things follow certain rules or patterns. In math, we call that an equation. And in class, you've probably seen some kind of, function that looks like this. It looks fancy, it looks scary. Why are there so many things in the bracket? All this is saying is that we can come up with rules, equations, to describe real world problems where these rules depend on certain variables. So it can have many, many variables. I'm going to give you some examples that most of you are already familiar with. You know your favorite Pythagorean theorem? That describes the relationship between the sides of right angle triangles, right? So the equation is, when you have a right angle triangle, we have c squared equals a squared plus b squared, right? Well, we could rearrange that, move everything to one side, and have the equation equal 0. That's why in the lecture notes textbooks, they always have the function equaling 0. That's the reason why. You're just moving everything to one side. And this relationship depends on 3 variables, c, a, and b, right? Another relationship is the weight or mass of something. That is given by the mass is the density times volume, right? So it depends on 3 variables, mass, density, and volume. That's the relationship between those 3. And I can rearrange them into an equation that equals 0. Okay, so that's all it's saying. That's a mathematical model. That's it. Now, for mathematical models, sometimes they're not going to give you these equations, right? If they're nice, they'll give it to you. But sometimes we have to come up with these equations. And how we do that is we first want to check and make sure that the equation makes sense. And one of the easiest ways to check if something makes sense is to use something called the dimensional consistency. How many of you guys have taken physics here? I think a lot of you guys, right? If you've taken physics, just put your hand up so I know. Yeah, majority of you. Great, amazing. So in physics, this is probably called dimensional analysis, okay? Dimensional homogeneity, same thing. So what this is saying is that the units in an equation have to match up on both sides of the equation. So for example, mass is density times volume. We know that relationship. So for example, mass could be measured in kilograms. Volumes could be measured in centimeters cubed or meters cubed, something like that. Then in this case, density, for us to have this match up, density has to be kilograms per centimeters cubed, because then the centimeters cubed cancels out with the centimeters cubed, and then we have left side of the equation equals right side of the equation. That's all this means, okay? Dimensional homogeneity, that's all that means. The units on each side have to match up. Same thing for this next one, and this next one is going to come in play later on when we're talking about applications of differential equations, right? When we're talking about administering drugs in your body, mixing it around, that kind of stuff. So what this is saying is that the mass of something, or the quantity, you can think of it that way, is the concentration times the flow rate times time. So for example, mass, again, I'll measure it in milligrams this time. Usually for this course, you're talking about some kind of drug. The concentration is the amount of substance per volume, right? So for example, milligrams per liter. Flow rate is how quickly something is flowing. So that's maybe liters per, I don't know, hours. Of course, it could be liters per second, milliliters per second, but I'm just giving you an example here. And then let's say time is in hours. In this case, the liters cancel out with liters, hours cancel out with hours, and we see that we have milligrams on each side of the equation. So it's dimensionally consistent. Okay, so we know this equation at first glance looks right. So the types of questions you guys could see on the test, and you've seen some variation of this on the weekly quizzes already, is something like this. Let's say you have the ideal gas law, PV equals nRT, and I'm telling you P is measured in atmospheric pressures, ATM, V is measured in liters, that's the volume, N is the number of moles, and T is measured in Kelvin, it's temperature, right? We want to determine the units of R, okay, to ensure dimensional homogeneity. So meaning that the left side of the units have to equal right side of the units. So in this case, what you're going to do if you're asked to figure out the units of something, solve for that variable in your equation, okay? So let's go ahead and solve for that. We have PV equals nRT. I want to find the units for R, so I'm going to get rid of everything else, meaning divide both sides by NT, right? We want to get rid of them. So I get PV divided by NT equals R. And now we can fill in the units. Well, P is ATM. V, that's in liters. N, that's in moles. And T, that's in Kelvin. So we just figured out the units for R. This is it. This is the units for R, okay? And again, you guys probably have seen this equation before in chemistry, and that's totally fine if you know what the units are, but they can give you some gibberish equation and give you units for certain variables and ask you to solve for the units for a missing variable so that it's dimensionally consistent, okay? All right. If there's any questions about this, let me know, but I feel like most people usually are okay with this. So I'm going to move on to the next part. In terms of topics today, I'm going to cover all the way up to differential equations, the applications of differential equations. I'll try my best to get there. I don't want to skip past things. So I'll try my best to get there, and whatever I don't cover, I'll cover next week. And next week, we'll cover the rest of the DE chapter as well, okay? All righty. So next topic is relationship between quantities. And this is all about definitions here, okay? So there's an equation that relates different variables, right? It tells us the relationship or the pattern between those variables. There's two major types of relationships that you guys are concerned with in this course, at least in the beginning, and that's called the isometric scaling, isometric relation, and the allometric scaling or allometric relation, okay? So what this means is that in an isometric relation, that's what I like to call it, the two quantities that are being related, they grow proportionally to each other. And that's modeled by y equals bx. It's your straight line, right? Y equals 3x, for example, y equals 4x, some number times x. It grows proportionally because, for example, if x doubles, my y quantity will double. If x triples, my y quantity will triple. So that's isometric scaling, okay? Allometric scaling, a little bit different. The two quantities grow disproportionately to each other. For example, you will have y equals 3x squared. So in general, if it's allometric, it has the form y equals bx to the m, where m is not 1, because if m is 1, we're back at our straight line isometric scaling, right? So y equals 3x squared, for example, is allometric. Notice that if x doubles here, if I put a number that's doubled into x, y doesn't just double. Why? Because, y depends on the square, right? So if x doubles, y actually quadruples, okay? So it doesn't grow proportionally. I think these two relations, probably the names, not a lot of you guys have seen before this class, right? But in terms of y equals bx, y equals bx to the m, a lot of you guys are familiar with that equation. What might be new is something called the log-log graph, right? That might be something new to you guys. So I'm going to cover that right now. So just looking at the general graphs, before I even talk about what the heck is this log-log space, log-log graph thing that they keep talking about, I'm just looking at the two graphs for isometric and allometric. Isometric is a line, y equals bx, right? So something that looks like this, a straight line right here. Y equals bx to the m, for example, 3x squared or 3x cubed, 3x to the fourth. What's going to happen is these values that are small when x is small, they're kind of gathered together. But then all of a sudden, the y value shoots up. It grows really, really quickly. So it's not a straight line anymore. And the problem with graphs like that is that they become really hard to read. So a lot of you guys, biological applications, right? That's what this course is about. So a lot of you guys are getting into the biological health field. For example, if you're taking blood samples from patients, you might think, oh, a lot of patients, their data is kind of grouped together. They do have little variation, but they're similar. But then all of a sudden you have these outliers. All of a sudden you have these people with, these points that are all the way over here, and you're not able to really see what's happening down here because it's kind of flat. You're like, are they really that similar? I can't tell because it skews your graph. So instead what we want to do is we want to zoom in. And the way to zoom in on a graph in math is to use the log or the natural log, okay? So we're going to use the natural log, which is ln. So if you've taken any calculus class, you've seen this ln before. That's just the natural log. And there's two ln rules that I need you to remember because we're going to use them to transform these graphs. The two ln rules are ln of AB, or log of AB, equals ln A plus ln of B. And the other log rule is ln of A to the R equals R times ln A. I'm allowed to bring the exponent down. So by using these two ln rules, now we can transform this equation. So this is an allometric relation, right? Y equals bx to the m. There's some kind of power on it. I'm going to take the ln of both sides. So ln this side, ln this side. But then we can use our ln rules to simplify this. So we have ln of y equals, now I have two things here, ln of a times ln of b. I can split them up into a sum. So this is ln of b plus ln of x to the m. Oh, but then I have an exponent, which can come down to the front, right? That's a ln rule. So this gives us ln of y equals ln b plus m times ln x. Great, now I no longer have exponents. And here's a trick that I use for myself so that I understand what's happening. Pretend you're replacing this ln y with like a y star or something. Call it a new y. Call this a new x. Then all of a sudden your equation is just y equals mx plus b. It's just a straight line. So we're able to turn it into kind of a straight line equation, okay? So I actually have a lot of students who asked me how these log-log graphs come about. I don't know if that's you, and I want to check with you guys just to see if I'm on the right track in terms of pacing. How many of you guys understand this part completely with what I just explained? Okay, thank you, thank you. I'm going to do some examples, don't worry. How many of you guys are like, no, not happening? What's happening here? Why are there lawns? Okay, thank you. Thanks for letting me know. Okay, so again, recap before we look at some further graphs. When you have two relations, y equals bx and y equals bx to the m, our whole goal is we want to turn these into graphs that we can zoom in and see what's happening. y equals b to the x, or sorry, y equals bx to the m looks like this. It's this massive curve, and this curve prevents us from really looking at the data that is all bunched together, these guys. So we use this trick where we ln both sides, turn it into a line, right? This is y equals mx plus b. For example, y equals 3x plus 5, right? And a line, it helps us zoom in and see what's happening, okay? So this course is all about definitions. They give it a fancy name. They call it an affine linear function. It's just a line. It's y equals mx plus b, right? Y equals 3x plus 5, for example. They just call it a fancy thing, affine linear function, okay? So now with this ln trick, we're able to create these log-log graphs or log-log space. So I'll show you these two graphs, and then I promise an example is coming. I'm gonna have you guys try some of it yourselves. So again, a log-log graph or log-log space is just a two-dimensional plot where instead of our axes being x and y like this, we now have our axes being ln x and ln y. So remember our trick, we take the ln of both sides, so ln y, ln b of x, and then we can split it up using our ln rules, and it becomes this guy. Well, this is our new y equals our 1x plus b. So it's a straight line, and the slope of this line is 1, and the intercept, or the y-intercept, is ln b, right? That's what happens when you turn y equals bx into a log-log graph. Nothing really fun there, it's just we're turning a straight line into another straight line. But what's very useful, what's really interesting, is when you have an allometric relation. So we have this kind of curve that just spits up and grows really, really fast. Again, we do the same trick. We did it on the last slide, right? The last page. We take the ln of both sides, and then all of a sudden, we end up with ln y equals m times ln x plus ln b. I just rearranged them. It's the same thing we did before, just rearranged. And this is now our new y equals mx plus b, which is a straight line. This straight line has the slope m, and the intercept, or the vertical intercept, of ln b, okay? So that's essentially what we're doing. And this helps us zoom in and actually see what's happening with our data points. All right, so let's take a look. I know some of you guys are eager, like, how are they gonna ask me questions on this? Let's see what types of questions they can ask you. And you've seen similar variations of these questions in the quiz if you already tried the quiz. So this question here, we have two random attributes that we're measuring, happiness and motivation. I totally made these up, okay? And let's pretend that happiness and motivation are modeled by the functions h of a and m of a. What this means is just we can somehow create a pattern for happiness and motivation using two equations, the h equation and the m equation. That's what modeling by an equation means, okay? Both of these equations are going to depend on some mystery factor A. I don't know, dopamine, serotonin, whatever. You guys are the biology people, you tell me. And they're telling us that this equation, h of a, is 3a to the fourth. M of a is a half a squared. And we want to use this to answer these questions here. So in part A, if we double the value of a, then happiness, meaning h, increases by what factor? So they're telling us we're doubling a, and they want to figure out what's happening to happiness. So I'm going to write down the happiness equation. It's h equals 3a to the fourth, right? And what we're doing is we're doubling this value of a. So I'm going to replace a with 2a. So we have our new equation, h equals 3. Instead of a, it's now 2a to the fourth. And if we simplify this, I can take 2 to the power of 4 and a to the power of 4 to break up this bracket. We get 3 times 2 to the 4, a to the 4. And this looks like our original a, doesn't it? The original a was 3a to the 4. This is just 2 to the 4 times 3a to the 4. So essentially what happened is we took our original happiness and we are multiplying it by 2 to the power of 4, which is 16. So that means that happiness increased by a factor of 16. Okay, so when a doubled, happiness didn't just double. it went up by 16 times. I want you guys to try part B on your own. So part B is if we have the value of A, so we cut it in half, what happens to motivation, okay? So do this same thing, do a similar thing, see if you can come up with the answer for B. And if you're done, if you can just raise your hand just so I know how many of you guys are done when I can take it up. Okay, I have more than half, majority people, I guess, have somehow indicated that they've tried it at least, right? I'm seeing some hands go up and down, up and down. So I'm going to quickly take this up so we can move on to some more questions. I want to expose you guys to as many questions as we can here. So this time we are having the value of A. Be very careful. They're asking for what happens to motivation. So don't use the H equation. You're using the M equation, the motivation equation. So M, or M of A, is 1/2 A squared. Just get rid of that so it doesn't look weird. And then I'm going to cut A in half. So I'm going to replace my A with half an A. 1/2 A. Okay, and let's simplify. Again, I can break up this bracket by squaring my 1/2 and squaring my A. So I get 1/2 squared times A squared. Again, this should look like our original M. It's differ by just a little bit. So I'm going to take out what looks different, which is this 1/2 squared, and then I still have my 1/2 A squared. So this is just my original M, right? So what's the difference? I replaced A with 1/2 A, and now my equation is multiplied by 1/2 squared, which is 1/4, meaning that when A gets cut in half, motivation decreases by a factor of 1/4. Okay. How many of you guys got that, just so I know where we're at? Thank you, amazing. And I'm sorry if I keep asking you guys to raise your hand. I just want to make sure you guys are with me. Like I said, it's a big class. Like I don't want to leave anyone behind and I don't want to go too slow. So really need your help here, okay? Okay, part C. Is the relationship between H and A isometric or allometric? Who thinks it's isometric? Raise your hand. Okay, who thinks it's allometric? Raise your hand. Beautiful. Thank you, thank you. The more you guys participate, the more you're going to get from these tutorials, I promise. So allometric means that it grows disproportionately, right? Disproportionately, I can't really spell, so bear with me, something like that. Isometric is proportionally, meaning it's like y equals bx. Isometric is y equals, bx to the m. So if you look at H and A, well, that's this right here, right? This guy. H is 3a to the 4th. There is an exponent on it. That's why it's allometric, okay? All right, now it's the fun log-log graph stuff. I know this is usually new for students. Whenever I'm tutoring people, they're always like, this is where I hit a wall. So if we're plotting the relationship between H and A on a log-log graph, what would be the slope and intercept of the resulting line? So if they're asking for slope and intercept in a log-log graph, well, we need to come up with the log equation first. So they're asking for the relationship between h and a. So guess what? We need an equation with both h and a in it. And lucky for us, the question told us what that is. Let me scroll back up. H equals 3a to the fourth. That's our relationship. So we're going to start there. Right? Then I'm going to take the log or ln of both sides. We usually just use ln. It's a more natural, get it? Because it's the natural log. So we take the ln of both sides. We get this. Okay. And then this doesn't really look like y equals mx plus b, but we can use our ln rules or log rules to separate this to make it look more like y equals mx plus b. So on the left, we still have a ln h. On the right, I can break this up. This is two things, ln of two things being multiplied turns into a plus, right? So now I have ln of the first thing plus ln of the second thing. And another ln rule, finally, helps us bring our exponent down to the front. So we have ln h equals ln of 3 plus 4 ln of a. So based on this, what is the slope and what is the intercept? Write that down. Write down the slope, write down the intercept. Okay. What is the slope, everyone? For those of you who know, help me out here. Thank you. Yes, thank you. A lot of messages coming in. Yes. So I'm seeing majority has something to do with, you know, a 4 or 4 ln a or something like that. Remember, your equation, we want this to mimic y equals mx plus b. Okay. So on the left-hand side, this is just ln h is by itself. So I'm going to squeeze this in here. This is going to be our y. This is our new y. Then on the right-hand side, where's the variable? Well, the variable's over here, so this ln a is going to be our new x. So this looks like our y equals, I'm just making this up here, some number plus some number times x. In the y equals 3 plus 5x situation, the number in front of x is our slope, and the number by itself is the intercept, right? So it's the same deal here. Our slope is the number in front of our ln a, because that's our variable, so that's our slope. And the number that's by itself, ln 3 is just a number, right? If you don't believe me, punch it in your phone, punch it in your calculator. Ln 3 is just a number. So that is your intercept, okay? Common mistake I've seen students make before looking at like past exams and stuff like that is the intercept. Some students say, oh, the intercept is 3. The intercept is ln 3. Don't let that confuse you. The whole ln 3 is a number, okay? Okay, part E, slightly trickier now. We have the logarithm of h, so the log or ln of h. They're telling us that that is an affine linear function. That's a fancy way of saying it's a line equation, okay? So log of h is some kind of line equation of the log of m, meaning that we get our new y equals mx plus b if we log both sides, right? If we were to plot ln h on the vertical axis and ln m on the horizontal axis, what would be the slope and intercept of the resulting line? So they're asking us to do the same thing as the last question. They're asking us to find slope and intercept, but it's a little bit fancier here because they want the relationship between h and m. And guess what? If I go back to my question, there's no single equation that relates h and m. That's what makes this question a little tricky. We need to somehow come up with an equation that relates h and m. So just so I don't have to keep scrolling and make you guys dizzy, I'm just going to write down the two equations. We have h equals, crap, I don't remember, 3a to the fourth. Sorry, said I wasn't going to scroll. And then m was 1/2 a squared, right? I believe these two are the equations. We need to somehow rewrite them in terms of one equation here. I want you guys to think about this, okay? Try to make an equation that just has m and h in it. And if you can get to that point, figure out what the slope and intercept is once you log both sides. I'll give you guys a minute or two to try this out. And again, if you're ready, if you're done, raise your hand, or even if, at some point, if you're like, I've gone as far as I can't figure it out anymore, just raise your hand just so I know when to start taking it up. But really give it a go. Okay. So give or take about a quarter of you guys are done. I know a lot of you guys are still working on this, and if I had all the time in the world, I would let all of you guys complete the question before I go through it. But I want to get through more of the even harder stuff later on, right? So I'm going to start taking it up now. Thank you for letting me know for those who are done. So the whole point is we want to come up with one equation that relates our h and m. Whenever they ask for slope and intercept, we need an equation that relates those two variables. Otherwise, we have nowhere to start. We have two separate equations here, but they do have something in common. They have this a in common. So what I'm going to do is I'm going to solve for the a in one equation, then use what you guys learned in probably grade 10, substitution, substitute it into the other equation, okay? It doesn't matter which equation you start with. I'm going to start with the second equation because it has a smaller exponent. It doesn't matter if you started with h. You could do that as well. You'll get the same result. But in this second equation, I'm going to solve for a. So first, I'm going to divide both sides by 1/2, meaning multiply both sides by 2. Then I want to solve for a. So I'm going to take the square root of both sides. Okay. I know there's technically that plus or minus thing happening, but I'm going to ignore that for now because you're going to see what happens. Now I have this guy. I'm going to substitute a equals the square root of 2m into my h equation. So instead of h equals 3a to the 4th, we have h equals 3. Instead of a, it's now the square root of 2m to the 4th. And then to get rid of the square root, squaring it will get rid of it, right? And raising something to the power of 4th is just squaring it twice. So this becomes 3 times 2m squared. And then simplifying this, 2 squared is 4, 4 times 3, 12, right? 12m squared. So now we have an equation that relates both h and m. If you did it the other way around, if you went for h and then you solve for a in the h equation, you'll get the same thing, all right? Okay. Now we have this equation, we can go ahead and find the slope and intercept of the log graph, right? Because we're plotting ln h and ln m on the axes. So I'm going to ln both sides. So I have ln of h equals ln of 12m squared. On the left side, that stays as ln of h. On the right side, we use our same trick. We break it down, boom, boom, So we have ln of 12 plus ln of m squared. But I'm going to use that trick where I'm going to bring the square, the exponent, I'm going to bring that down because that's another ln rule, right? I'm going to bring it up to the front. And now we have our new equation, quote unquote new equation. This is our new y. This is our new x. So we have y equals mx plus b, a straight line, okay? And we can pick out what the slope and the intercepts are. So the slope is the number in front of our x variable, so that's the number 2. And the intercept is the number that's by itself, so that's the ln 12. Okay. Someone's asking, can we ln both functions first and then isolate for the ln a? Yep, you could. There's different ways to solve this. I just find from my experience working with students, this is the most intuitive way that students usually find it. They understand it more, but feel free if you can do it another way, as long as you get the same answers, you're good to go. Why did we do the ln part? Yeah, absolutely. So this step right here is the key, right? Once you come up with an equation with h and m or whatever two variables they want you to relate, be very careful. They're not asking what is the slope in the graph of h equals 12m squared. They're asking what is the slope and intercept when we plot ln h against ln m. So we're no longer going to have a graph that's h and m. Those are not our axes. Our axes are ln h and ln m. That's why we have to ln both sides so that we get these two variables, ln h and ln m. Okay? Okay, so that's log graphs. Now I want to go into recursion. I'm going to quickly go through at least one more little part of recursion, and then we'll take a short break. I don't expect you guys to be able to sit for 2 hours, don't worry. I'll give you guys a break in just a second. Just want to cover some of at least the definitions for recursion. So what is recursion? Recursion is when the new thing depends on previous things. That's pretty much what recursion is, okay? But in math, it's a little bit more defined. In math, a recursion model is an equation that defines a sequence of values, so the next value, the next value, the next value, based on previous values, okay? So for example, the Fibonacci sequence, most of us know what that is, right? We have a sequence of numbers. It starts with a 1 and a 1, and then we add the previous 2 to get to the next one. And then we add the previous 2, 1 plus 2 gives us our 3. We add the previous two numbers, 2 plus 3 gives us the 5, and then 3 plus 5 gives us the 8, and so on. So the next number depends on previous ones. We can come up with an equation for this. In general, any t number, ut, this stands for the tth term. So if it's u sub 10, that's the 10th number. If it's u sub 20, that's the 20th number. The tth number is the previous number, so u sub t minus 1, plus the one before that, u sub t minus 2. Okay, so that's a general form for the Fibonacci sequence. And notice that they have to tell us where these sequences start. Another example is the factorials. N factorial, this little exclamation mark, means I'm going to have n times n minus 1, n minus 2, all the way down to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. And the terms in the factorial depend on previous terms. So if I wanted to find the nth term, like the 10th term or the 20th term, that's actually the n, whatever number n is, times the previous term. So for example, if I want u sub 10, the 10th term, that is 10 times u sub 9. It's 10 times 9 factorial, where the first term, or the 0th term, the starting term, is 1, okay? So it's very clunky, though. Recursion models do look very clunky, and if I wanted, for example, the 157th term, I would need to know what the 156th term is, and I would need to know what the 155th term is, and so on. So recursion models are really hard to use. Instead, we want to come up with a nice formula where we can just plug in 157 and figure out what the 157th term is. That's the whole idea behind these recursions. And this example illustrates that, I think. If you have the population of bunnies, bunnies like to procreate, right? So we have the number of bunnies grow really, really quickly. Starts off in the beginning at 2. So at year 0, there's 2 bunnies. U0 is 2. Then it doubles into 4. So that's year 1, there's 4. Year 2, there's now 8. Year 3, there's 16. Year 4, there's 32, and it just keeps doubling. So in general, the t plus first term, so the next term, is 2 times the previous term, right? It doubles. But we can also write that as 2 to the power of t times the initial number, which is 2. And that will help us get to any term we want. That is much more useful. This equation is much more useful because now we can just plug in, hey, I'm going to plug in 100. Plug in t equals 100. U of 0 is 2. And we can calculate how many bunnies there's going to be 100 years from now. Okay, so that's a whole idea behind recursion. We have the general form of a recursion model. The next term depends on the previous terms. So it's a function of the previous terms and some t value. And they have to give us the initial value. It's very clunky. We don't want to use the recursion model. Instead, we're going to come up with something called the explicit form, or the explicit solution of the recursion model. And that is one super nice formula where it only depends on the initial value, so how many bunnies there were to start off with, and some function of t. So I can just plug in t, and then I can find what how many bunnies there are at any given year. Okay. The types of questions they're going to ask you with recursion model, you guys have seen it probably on the quiz already. There's population models and investment problems, because both of these grow really quickly and or decay very quickly. So they usually like to use recursion models for these. There's 2 common types of recursion models. There's the simple one. Yay, simple ones are super nice. And then there's the complex one. The simple one looks like this. And I apologize if my notation's different than your TAs or your profs. I know some people use Ys, some people use Ps, some people use Us. So I'm using U here, this U. If you see Ys or Ps, it's the same thing, it's just another letter. U sub t plus 1, so the t plus first term, is a times the previous term, okay? Where the initial one is U0. These ones are super nice. We'll look at them in just a second. And then what happens is the instant they add a b, so it's the same equation, u sub t plus 1 equals a times u sub t, but now they're adding this evil little b, it becomes more complicated, okay? Just real quick definitions here. When you have recursion models like this a is either the growth rate or the decay rate. If a is bigger than 1, then it's growth. Think about it this way. If I have u t plus 1 equals, think of a number bigger than 1, for example, 3, u of t, u sub t. That means that the next term is going to be 3 times the current term. So it's growing, right? But if all of a sudden I change my a value to a number less than 1, for example, 1/2, then the next term is a half of the current term. So it's decaying, it's dropping. That's why if a is bigger than 1, it's growth. If a is less than 1, it's a decay, okay? And then in the complex case, we have this plus b. If b is positive, we call that an input, because adding something will make the next term bigger and bigger and bigger. But if b is negative, that means we're subtracting b. That's a withdrawal, or it's really sad, but in the animal terms, it's a harvest. For example, if you're fishing, if you're removing things from the fishing pond, that's a subtraction. So that's called a harvest, right? So that's what these guys are called, okay? Why don't we take a quick break? Then I'm going to come back and show you how to find the explicit solution, which is the useful solution, for both the simple recursion model and the complex recursion model. Let's take a 5-minute break, and we'll resume at 6:20. I'll give you 6:27, let's say that. I'm going to post the survey link in the chat. Please, 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 please fill it out, because we want to try to find the best time for the majority of students to host these sessions, okay? So that we can release it and you guys can start signing up for next week's tutorial. Is this the link? Oops. Okay, so I just posted in the chat. I would really appreciate it if you guys fill that out. If you have feedback for me, put it in there as well. I just want to make these sessions better for you, okay? If you have questions, let me know. I'll be here during break. If not, I'll see you guys in 5 minutes. scroll back up to the example. Yep. So the example, I'm not sure which example. I'm assuming this one. If not, let me know. I can keep scrolling. Awesome. Great, great, great. Is the course this year Someone's asking, is the course this year harder compared to other years? It depends on who you ask. In previous years, for example, they never focused on recursion. I'll tell you when we get to the recursion part. But they also went a little quicker. So yeah, so it really depends on, you know, what is your Achilles heel for topic-wise. Will this tutorial be recorded and sent to us? Yes, if you have class, I don't want to hold you up. The tutorial this week will definitely be sent to you. All subsequent tutorials will not. That's why we're trying to find a best time for you guys, okay? So if you can fill out the survey, select as many times as you are available, not just your preferred one, because we want to find a time that really works for everyone, and then we'll release those times, okay? But the tutorial today will be emailed to you. Yeah. For the simple and complex recursion model, I'm going to go back down for a second. So right here, for the simple and complex recursion models, do the A and B values always represent the same thing? Yes, but it depends on the context. So like I was saying, for example, this B right here, let's pretend B was negative, like negative 500. If I'm talking about money, if I'm talking about investment, negative 500 means that I'm either losing $500 or I'm withdrawing $500 from my bank account. Whereas if I'm talking about population like fishing, minus 500 means that I'm taking out 500 from the fishing pond or whatever that is, right? So B is always either an input or a withdrawal from your population, from your big group. A is always the growth and decay rate, okay? Yeah, no problem. Will the recording be sent to you via email? Yes, so we will email you. It takes a couple of days for us to process the recording, so we'll email you the recording in a couple of days. But if you have any immediate questions after the session that you want to ask, just email me, okay? So I'll release my email again at the end of the session, but just email me if you have any specific questions you want to ask me. This is actually, so a question came in about the format of the exams and the midterm tests. In the past, yes, some years the exam and the midterm tests have been multiple choice. This year, a lot has changed, okay? So this year, for example, you guys have 2 midterm tests and you guys have, I think, essays, participation quizzes, and the exam. I've heard rumors that the midterm test may be multiple choice, but from my understanding, it hasn't been confirmed yet. So if any of you, I'm relying on you guys. This year, everything's changing. So if any one of you hears about the format of the exam or any information about the exam, midterm test, please email me so that I can tailor these to what you guys need and I can share it with your class, okay? But my understanding is that there was talk that it could be multiple choice, but it hasn't been confirmed yet. Do we need to register every week or is it just the one-time registration? You do need to register. Don't worry. I know this is a little messy because this is our first time running this, but after today, after we review all of your survey responses to see what's the best time or what's available times for everyone, we are going to open up registration for all of the weeklies and we'll send you an email to remind you to register, all that kind of good stuff. Okay, so don't worry, we will email you. Any advice on approaching the essays? I'm not going to lie, I'm going to be completely honest. I don't know what these essays are really about. When I read about them, I'm like, I don't know what this is. So I'll do a little bit more investigation to see if I can find out more and maybe share some insights next week. Okay, sorry, I don't have a more straightforward answer for you. Will these tutorial courses be free? So the first 1 to 2, so this week and next week will definitely be free. And then afterwards it would be paid, but I don't know what the price is yet. We'll release it on the site and everything for you. So if you have feedback about that, put it in the survey as well, because Robbie reads them so that he can help determine what's the best option for your class. Will this be Python heavy? This is another thing. When I tutored this course with students before, I've received 0 Python questions. So this year, I know it's a little different. I will not personally be covering Python just because I don't have the knowledge. But if you have specific question, I have used Python myself before, but not specifically in biological applications. So if you just have simple Python questions, email me privately. But anything more complex about, application questions, I probably won't be able to help you. Sorry. Okay. So yeah, this tutorial will not cover Python. Okay, lots of questions, but let's dive right back in because I want to go through the recursion stuff. Oh, last comment. Someone mentioned that they heard Python is not on the exam, just in labs. So if that's the case, great. You just need to know them for labs. Okay. All right, so explicit solution for the simple recursion model. So again, reminder, simple recursion model, that is when our next term equals A times the previous term. There's no plus B. There's no plus B minus B. These ones are simple. These ones are really nice because let's see what happens here. When t equals 0, so I'm literally just going to plug in t equals 0 here, I get u sub 0 plus 1, which is 1, equals a times u of 0. Okay? Okay, what happens when t equals 1? Well, I'm going to plug in 1 wherever I see a t. So that becomes u sub 1 plus 1 is 2 equals a times u of 1. But wait a second. U of 1 is just a times u of 0. So this is a times a u of 0. So this is a squared u of 0. Okay. When t equals 2, we do the same thing. Plug in t equals 2. So this guy is now a 2. So 2 plus 1 is 3. A u of 2. Well, wait a second. U of 2 is a squared u of 0. So this is a, oops, change my color back, times a squared u of 0. So this is a to the power of 3 u of 0. So some of you guys can already see the pattern here, right? I'm going to highlight it for us, just emphasize it. U sub 1 is a to the power of 1 u of 0. U sub 2 is a to the power of 2 u sub 0. A sub 3 is a to the power of 3 u 0. So guess what? The next one is going to be u4 is going to be a to the power of 4 u 0. So in general, the explicit form is just going to be u sub t equals a to the t u sub 0. That's it. So highlight that, box that, write that down, okay? That is the explicit solution for the recursion model. So we now no longer need to rely on this silly little recursion model that's super hard and tedious to calculate. We now have this direct formula. We can plug in t equals whatever number and figure out what that term is, okay? Good question. Is A the same thing as lambda? Yes, they could use the letter lambda. They can use the letter K. I've seen the letter C, but I think looking at your notes this year, I think the majority is either lambda or A. So whatever letter that is, that's the same thing. It's your growth rate, decay rate, whatever that is, okay? Now, I just want to make something really clear because it's going to really help later when we do the complex case. U sub t equals a to the power of t u sub 0. This t is just a variable. It's just a letter. So essentially, u sub smiley face equals a to the power of smiley face u sub 0. I can put whatever in there. I can put u sub t plus 1 equals a to the t plus 1 u sub 0. Whatever I put in that smiley face, it just has to be the same. That's the explicit form, okay? All right, let's look at some questions that they can ask you using the simple form. So we have an investment. So we want to grow our money. An initial investment of $1,000, they're telling us that it increases in value by 10% each year. So it's growing here. So our A value or lambda value should be greater than 1. We know that, right? So we want to create a recursion model, represent the amount of investment. So think to yourself, okay, if this year I have $1,000, what will I have next year? Well, it's going to increase by 10%. So if I wanted the amount in the next year, that's going to depend on how much money I have this year, and it's going to grow by 10%. Common mistake I see students make is they write 0.1. Don't write 0.1. 0.1 is less than 1, meaning that it's decaying, it's decreasing. That's not true. Our investment is increasing, right? So it's not 0.1, it's 1.1, because what happens is we need to multiply our entire investment by 1 plus the 10% increase. So it's 100% plus the 10%. That's why it's 1.1, okay? Don't make that mistake. And then in part B, we want to write out the explicit solution to this recursion model. Well, this is your A, or lambda, whatever you want to call it. And our explicit solution is u sub t equals a to the t u sub 0. So I'm just going to replace a with 1.1, and u sub 0 is the initial amount, so 1,000. So the explicit solution is u sub t equals 1.1 to the power of t times 1,000. And now this is a badass formula, because now we can just plug in whatever t value and figure out how much money there's going to be at that year. Okay. Part C, when will the investment be worth more than double the original amount? Okay, the original amount was 1,000. So double the original amount is 2,000. So we want to figure out when the investment will reach $2,000. When we'll have $2,000 in the bank account. Well, we have the formula, so we're going to use it. We're going to substitute the 2,000 in for u sub t. And we want our investment to be worth more than this. So for those of you who like to use inequalities and want to be fancy, feel free to put an inequality sign like this and then put your equation in. I know a lot of students get confused with the inequality. They're like, when do I flip it? So you know what? I'm just going to stick to an equation. Just keep it as an equal. And then at the end, we'll reason it out. Okay? So we want to solve for t. Okay. T is over here. We can't deal with that t yet because we have to get rid of the 1,000, right? Just solve it like a normal equation. Get rid of everything furthest away. So I'm going to divide both sides by 1,000. Dividing by thousands is super nice. Just cancel the zeros. So 2 equals 1.1 to the power of t. Now we need to bring this t down. We don't want it as an exponent anymore. So think back to all your calculus stuff or all your high school math stuff. If you have your exponent in, or sorry, if you have your variable in your exponent and you want to solve for it, your best friend is your ln. We're going to take the ln of both sides. So we end up with ln of 2 equals ln of 1.1 to the power of t, because now we can bring that t down using our ln rules once again. Okay, so this is ln 2 equals t times ln of 1.1. And then finally, solving for t, we're just going to divide both sides by ln 1.1. So that means that when t is ln 2 divided by ln 1.1, whatever this number is, the investment will be worth $2,000. But we want it to be more than $2,000. So if you were writing a final statement or something like that, you would say when t is greater than whatever this number is, that's when your investment will be worth more than double the original amount. But I know that for your quizzes, for example, you just have to type in the number. You don't need to worry about the inequality sign, right? A question, is it possible to take the log of both sides instead? Absolutely, you can take the log of both sides if you want. The only difference is ln is a special base. Ln is actually log base e. Whereas if you take the log of both sides, that's log base 10. Okay, it's the same thing. You can, if you want, you can take log base 5 if you wanted to, but no one does that. It's either ln or log, same thing. Okay. Okay. Let's move on to another question so that we can jump into the complex case. Half-life. You need to know half-lives in biology and chemistry, all that sciencey stuff, right? The half-life of a substance is 60 years. What that means is that the amount of things inside your petri dish or whatever gets cut in half every 60 years. It gets cut in half again, another 60 years. And another 60 years, it gets cut in half again. Okay, so it just keeps getting cut in half. Suppose that there was an initial, sorry, that's a typo, there was an initial 500 grams of this substance. Okay. We want to write down a model for the relationship between time, t, the number of years since the initial amount, and A, the amount of substance. So they're not telling us that every year the substance gets cut in half. If that's the case, we can write out the recursion model. But that's not what they're saying. They're saying that the substance gets cut in half every 60 years. So we're not going to use the recursion model here. We're going to jump straight into the explicit solution, the explicit form. Remember, the explicit form was u of t, equals a to the power of t u of 0, right? That was the explicit form. We're going to jump straight here. But now I'm going to substitute what I know. Well, I know what the initial amount is. They told us the initial amount is 500. Okay, so we know U0 is 500. I'm also going to replace this U sub t with what they want, which is A. They don't want to call it U sub t, they want to call it A, the amount of substance. Okay, so I'm just going to rewrite my equation. A equals A to the power of t times 500. Now we're almost there. They're asking us to write a model, meaning an equation. This equation is almost there. We have A and we have T, but we still are missing this little growth rate or decay rate, right? But the question gave us more information. They told us that the half-life of the substance is 60 years, meaning that when T is 60, we should only have half of the original amount. So I'm going to put that in. When T is 60, the amount is now half of the original. So half of 500, which is 250. So let's plug that in. So A is 250 equals little a to the power of t, which is 60, times 500. And guess what? We want to solve for a, because if we can solve for this little a, then we can put it into our equation and we have a full equation, which is the model they want. So now let's solve for this a. Do the same thing as you did before. Get rid of the things that are furthest away first. So let's get rid of this 500. 250 divided by 500 is 1/2, which makes sense because it's a half-life. A to the power of 60. And then from here, there's two ways for you to solve for your A. I'm going to go with the same way that we've been doing before, which is take the ln of both sides. Again, you can take log if you want to. So we get ln of 1/2 equals ln of A to the power of 60. But then good news, we can bring this down to the front. So we get ln of 1/2 equals 60 times ln of A. So I'm just going to continue it over here so I'm not squishing it. Keep solving for A, right? We're just solving the equation. So let's divide everything by 60. And one final step, we want to get A by itself. How do we get rid of a ln? How do I get rid of the ln that's in front of the A? Any ideas? Yes, thank you. Yep. Thanks. Thank you. I'm getting a lot of responses in both chat and Q&A. saying E. Yes, the nemesis of ln is E. They're enemies. They get rid of each other. So I'm going to E both sides like that. So we have E to the power of ln of 1/2 divided by 6 equals E and ln cancel. That's an A. Okay. So therefore, the model that we want, remember, go back to your original. This is the model we want, but now we're going to replace A with this ugly E to the something. So A is going to be E to the ln 1/2 divided by 6 times 50, or times 500. That is your model here. Okay. Oh, sorry, 60. I dropped the 0. Thank you. Thank you for pointing that out. My bad. Thanks. Okay. All right. Okay. So that's how we come up with our model. Oh, thank you. Sorry, I forgot the T as well. Thanks. You guys are catching me. That's great. Just making sure you guys are paying attention. No, I just missed that, honestly. All right. So that's your model. And then they're asking, when will the amount of substance be less than 100? I want you guys to solve this one on your own. Try this out. Figure out when the substance will be less than 100 grams using the model you found. Okay. Okay, hopefully you guys had a chance to try this out. I know some of you guys are still writing it down, and I'm so sorry to do this to you, but I really want to get onto the other things as well, right? I want to get as much explanation as I can in this session. I'm going to take this up. So when will the amount of substance be less than 100 grams? 100 grams, this is an amount. So we're going to plug it into our A. So we have 100 equals E to the ln 1/2 over 60 T times 500. It's messy, so messy. And I'm getting a lot of questions saying, is there a way to simplify this into a simpler form like we've seen in high school? I'm going to show you how to do that in a second, but let's focus on this question for now. I'll get back to it in a sec. So we want to solve for this T that's buried inside, oops, sorry, wrong pen, buried inside the exponent in E to the power of something. So get rid of the things that are furthest away first. Let's divide both sides by 500. So we get a fifth equals E to the power of ln 1/2 over 60 times T, right? And then solve away, peel away the layers like an onion. We want to get rid of the outside layer. T is wrapped inside something, E to the power of something. So we want to get rid of the E. The opposite of E is ln, right? So I'm going to take the ln of both sides again. Ln and E are really nice. When they're side by side with nothing in between, no interruptions, we can get rid of them. So I cancel them out. And now I'm left with ln of 1/5. And on the right, we have ln of 1/2 over 60 times t. Ln of 1/2 over 60. This is just a number. I know it looks messy, but it's just a number. If you put in your calculator, you get some kind of decimal, right? So since it's just a number, we can divide by it. And when you're dividing by a fraction, flip and multiply, right? So you multiply both sides by 60, divide both sides by ln 1/2. So you end up with 60 times ln 1/5 divided by ln 1/2. That is your t value. So the amount of substance will be less than 100 grams when t is greater than this number. So after this many years or whatever unit of time, the amount of substance will be less than 100. Now, a couple students are asking, is there a nicer form? Because in high school, for those of you who remember your high school math, remember seeing a nicer form. And yes, if you know your half-life formula, all that stuff, there is a nicer form. And I'm going to show you how to get to that just real quick. It's not a requirement for this course. I've seen profs leave equations like this before. But if you want to know, I'm going to show you how to do that. Remember, E and ln cancel each other out when they're side by side. Okay, so this is kind of like as an aside. Let's do that. The problem is this E and this ln are not side by side. They're separated by this 1 over 60 business. So I'm going to rewrite this as A equals E, and then I'm going to separate this out. I have this T divided by 60. So I'm going to write this as T over 60 times ln of 1/2 times 500. Okay. And then use your ln rules again. Your ln rules are so powerful in this course. You keep using them. T over 60, that's a number times ln of 1/2. I can bring this up as an exponent using my ln rule. So this is A equals E to the power of ln of 1/2 to the power of T over 60 times 500. And the beauty of this is that E and ln are side by side now. They cancel. So we have A equals 1/2 to the power of T over 60 times 500. And I know some of you guys are like, oh, there's the form that I remember and love. So that's how you get to it. Okay, a lot of manipulation. So hopefully that answered that question. Okay. If there's any questions, just let me know in the Q&A and I'll get to them in a sec. Okay. All right. Okay, I'm going to move on now. We have still a lot more to cover. I'll try my best to do it justice. So now we have the explicit solution for a complex recursion model. This is where this course this year really changed quite a bit. In the past, they don't focus on this at all. They literally just tell you, okay, the general form for the recursion model, the complex recursion model, is this guy. U sub t plus 1 is a times u sub t plus b, and they give you the initial amount. And in the past, what they have done is they just gave you this formula. They said, hey, the explicit form is this. And literally you just plug your numbers in and that's your explicit form. They don't even bother with the proof or anything. They gave the proof as optional, but this is what they used to do. I know this year I've seen some of your tutorial notes. I've seen some of your handwritten notes. Profs seem to be going through the steps. So I'm going to go through the steps with you once. But since the midterm test hasn't been confirmed whether it's multiple choice, if it's multiple choice, I encourage you just memorize this, right? Memorize this explicit form and then you can just use it. I promise you that if the test is not multiple choice, in future weeklies and in the crash course before the tutorial, I'll come back and hammer out the details for the broken down steps. But for this tutorial, just to save time, I'm going to go through these broken down steps once. And then from now on, I'm going to just use this formula. Okay, so this formula is super handy. So we're going to follow an example here. We want to find the explicit solution to this complex recursion model. 1.5 times u sub t plus 100. And u sub 0 is 20. I'm going to show you how quick it is to use that formula. To use a formula, I just need to find my different pieces. I know that u sub 0 is 20. This is my a, 1.5, and my b is positive 100 because it's being added. So if I wanted to just use this formula, I can say that u sub t equals my u sub 0, which is 20, minus my b, which is 100, divided by 1 minus a, 1.5, times a to the power of t, plus b divided by 1 minus a. It's a painful formula. It's massive. But it's kind of like back then when you learned the quadratic formula, you know how it takes care of everything that you can't factor or you don't have to bother factoring? Same idea. And then you can simplify this. I'm just going to do it just to show you that it's the same answer in the end. We have, if you simplify what's in this bracket, just to save us time, I'm just going to quickly do it. If you want to confirm using the calculator, you can do that. But this should be 220 times 1.5 to the power of t minus 200. Okay, so I'm telling you, this is the answer you're going to get. But now I'm going to show you how to break it down using the steps. Okay, here we go. The steps are tedious, and I think most of you guys are struggling with recursion because there's so many steps. So step 1, we are going to solve for u sub t, in the equation u sub t plus 1 minus u sub t equals 0. So let's go ahead and do that. So I have u sub t plus 1 minus u sub t equals 0. Well, u sub t plus 1, they gave it to us in the question, right? This guy right here is 1.5 u sub t plus 100, and then minus u sub t equals 0, and we're solving for this variable u sub t. So let's group like terms. We have 1.5 turtles minus 1 turtle. That's how I like to think about it. So we're left with half a turtle. So 0.5 u sub t plus 100 equals 0. And then we solve for u sub t. So move the 100 over, becomes negative 100, and then divide both sides by 0.5. Boom, that cancels. So we have u sub t is negative 100 divided by 0.5. That's the same thing as multiplying by 2, right? Dividing by half, we flip and multiply. That's multiplied by 2. So this is negative 200. So we know that our u sub t is negative 200. Most profs and most TAs are going to call that u star or p star, y star, whatever variable they use. I'm going to keep that in my box, keep it handy for later. And then we want to create a new variable, okay, this x sub t thing. So I'm going to create it. And specifically, x sub t is going to be u sub t minus this u star. So I'm minusing negative 200, meaning I'm adding 200. Okay, so again, keep that handy. If you want, you can write it. I like using this box method because then it gives me space to write down things for later. So I'm going to keep it there. And I'm also going to solve for my x sub 0 because I'm going to need it later. So I'm replacing t with 0, or yeah, t with 0, sorry. So then I know that u sub 0 was 20. So 20 plus 200 is 220. So again, keep that on the side. We're going to need it later. So you can kind of already tell this is a really tedious process. So I'm just going to show you this once. Okay, part 3. Step 3, we want to write down the equation. Remember my whole smiley face rule? We have this equation here, x sub t equals u sub t plus 200. I can replace t with whatever I want. I can replace it with a smiley face. I'm choosing to replace my t with a t plus 1. Negative 200, there we go. Okay, which I can write this as plus 200 to negative, so I'm just going to put plus, save me some space. But wait a second. U sub t plus 1, this was given in the initial question. U sub t plus 1 is this 1.5 u sub t plus 100. So I can actually put that in there. Okay, so this is u sub t, sorry, one second, what was it? 1.5 u sub t, my bad. Put that in. Plus, oh, my memory's so bad. Is it plus 100? Yes, sorry, plus 100. So I'm replacing that with whatever was given in the question. And then plus 200. Now I can simplify this a little bit. This is 1.5 u sub t plus 300. And now this is where the trick happens. Without this trick, we won't be able to come up with the explicit formula. The trick is you want to factor out any common factors you see. So we have x sub t plus 1. This 1.5, I'm going to factor that out to the front. And by doing that, I'm left with u sub t plus 300 divided by 1.5 is 200. And this should look very familiar, and this will happen every single time when you follow these steps. You're going to end up with the x sub t that we have originally solved for in the last step. So now we have something fun happening. We can replace this with x sub t. Oh, that was a lot of work. I hate these steps. If it was up to me, I would make this multiple choice so you guys can just use the formula. Okay, so we got up to this point. Now it's the final stretch home. We've seen this before. This is the simple recursion model that we've done some questions with already in the last section, right? This is a simple model where I don't have that plus b. It's just a times u sub t or x sub t. So now I can write down the explicit solution. Remember, the explicit solution was x sub t is a, which is 1.5, to the power of t times x sub 0, and we calculated x sub 0. That was our 220. So we have that times 220, and that is an explicit solution. We've done all the hard work. Now the last part is the question started off with u sub t, right? Question was find the explicit solution for u sub t. We can't give them x sub t. So we're going to go back. Where was my, sorry, one second. I'm even losing track of some of these steps. There it is. Sorry about that. We knew that x sub t was u sub t plus 200, right? That was what we knew. So if we wanted to rewrite it as u sub t, I'm going to subtract 200 from both sides, so it's x sub t minus 200. So our u sub t, finally, our explicit solution is 1.5t times 200 minus, or sorry, times 220. Why did I put 200? Minus 200. And that's the explicit solution. All that work, those sweat and tears, notice that it's the exact same solution as we got if we just use the formula up here. So please don't make me do that again. Let's just use the formula. If it's multiple choice, memorize the formula for me. It will save you so much hassle from going through the steps. Okay. Okay, I'm going to quickly answer some of these questions here. In step 1, the 1.5 and the 0.5t. Yep, absolutely. So in step 1, notice that we have 1.5 of something minus 1 of something. So 1.5 minus 1, that's how we got this 0.5. Okay, let me know if that makes sense. How did we know that a was 1.5? Yeah, we just have to know the forms of these things. That's why I put them in those boxes for you to kind of memorize. When they give u sub t plus 1 as a recursive model, a recursion model, whatever number is in front of your u sub t, that is your a. So that's how we know that a was 1.5 in this question. Okay, yep, I'm going to scroll back down. Sorry, I scrolled up too early. Here's the chart. No problem, please memorize the formula. Actually, I want to see a show of hands. A show of hands if you've seen this formula in class, just so I know. Some of you, but not all, eh? Okay, So at least some of you have seen it. That's good. If you haven't seen it, highlight that, box that, write it on a sticky note, memorize it. Okay, you need it. The annotated document will not be given to you, okay, but the recording will be available in a couple of days. If you don't know the formula, you could use the steps, but honestly, would you rather memorize 5 steps or memorize the formula? So if you're not asked to show your work, if it's just, you know, multiple choice, just use a formula. That's what I would recommend. Okay, and real quick, let's go through this last step because someone had a question about this one. So this last step here, I know this one was where, oh, there's magic happening. So I'm going to go back to step, where was it? Step 2, okay? In step 2, remember how we wrote down this guy? X sub t equals u sub t plus 200. So I'm going to write that down again. From step 2, x sub t equals u sub t plus 200. That's what we got. And now I just rearranged it. I moved the 200 to the other side, so it's minus 200, and I got u sub t by itself. So that's exactly what we did. So u sub t is x sub t, which is this guy, minus 200. Okay. Tyler, awesome. So if you have the TA Tyler, he's great. I've seen his notes too. He's really organized. So if he's shown you he's shown you this formula, which is great. If not, copy it down. Okay, I just want to make sure everyone knows it. Thank you. Okay. Let's go on a quick 5-minute stretch break, and then we'll come back and do this. I don't think I'll be able to get to DE applications, but I'll at least get into solving some DEs with you guys. Okay. Promise I'll get through as much as I can, but I don't want to lose you guys in these tutorials. So let's take a 5-minute break, come back at 7:10. We'll power through, get through as much as we can in this week. If there's more questions, let me know. And if you haven't filled out the survey already, please, please, please fill it out. I'm going to put it in the chat one more time. Okay. There we go. Okay, so if you haven't filled out the survey, make sure to fill it out so that we know what's the best time for all of you. Okay, answering some questions here. There's a quiz question asking to find the equation for t minus 1. How would we do that? Yeah. Once you have the explicit solution, whether you like using the steps or the formula, once you have this, remember our smiley face thing. I can replace t with a smiley face. I can replace t with an elephant. I can definitely replace t with a t minus 1. So I could do that as well. I'm just changing my terms here. Okay, let me know if that's what you're asking. If not, I can answer it again. Someone's asking about the answers for this. So the recording will be sent. The answer, I'll think about whether or not to send the answer for the rest of the booklet. Let's see how far I get today. But if not, I am going to cover it in next week's tutorial as well, which is also free. So I'll let you know by the end of the session what I'm going to do with solutions, okay? Okay, I'm going to go back and answer some half-life questions. Can we use a general rule? So the student who's asking about the general rule for half-lives, yes, if you know the half-life equation, absolutely, especially if it's multiple choice, they're not going to ask for work. If it is multiple choice, you can just use that formula. Oh, yep, if you know the half-life equation, use it, okay? It won't break, it'll work. Recursion model for the investment problem. 1 second. I think it was this question, right? I think that's it. Let me know if that's the one. Are these tutorials going to be replacing the sessions before a midterm or exam? No. So for those of you who are used to the Wise or Beat Your Course style crash courses, we will still have those before the midterm tests and exams. The reason why we decided to go with tutorials is because, as you know, there's so much little details. So in tutorials, these things, I'm going through them much slower than I would be if I was going through a crash course. Before a test and exam, the crash course, I'm just going to focus on questions and really just do a bunch of them. But here I'm actually explaining, hey, you can use the steps, you can use the formulas. I'm showing you how to solve every single piece of equation because it's more, my hope is to keep you guys up the entire semester, okay? Write the, write the general half-life equation. Yeah, I need to think about it a little bit, but I'm hoping this is good. I'll go down here. So if you want, I don't use it, so let me think about it for a second. The amount at time t is the original amount times 1/2 to the t, or yeah, t over whatever the half-life is. And I know there's a ln version of this as well, but this one works as your general half-life formula, okay? I noticed that for the half-life question, if we simplified, we would have ended up with the same thing, okay? So if you wanted it, there it is. Will the exam preps and midterm preps be free or paid? I believe those ones are paid, but I would have to check with Robbie. So if you want to know right now, just send Robbie an email. Those ones haven't even been scheduled yet. Someone's asking, if you attend these weekly tutorials, do you need to attend the ones before the midterms or exam, like those crash courses? It's up to you, really. The tutorial, I'm going through everything in more detail, with the exception of the first and second week, because I'm trying to catch you up from the 2 weeks that we didn't have weekly tutorials. But the sessions, the crash courses right before a midterm and exam, I'm going through as many past exam-like questions as I can find, really just giving you guys, use this when you see these questions, do this when you see these questions, and we're just doing questions. Whereas here, I explained how these log-log graphs came about. I explained how certain things work out. It's a little more detailed in the weeklies. So it's really up to you. I recommend going to both just so you get the practice, but I get it if you guys are busy working on other things. If you don't have time to go to one or the other, at least go to one, okay? Okay, let's continue. We left off on page 10 and we wanted to find the explicit solution to this recursion model. And don't make me use the steps, please. I'm just going to use the formula. But like I said, if you guys find out, hey, actually it turns out the midterm test is not multiple choice and my prof said I need to know the steps, then I'll go through that with you guys at another weekly. But for now, let's use the formula. Okay, so we want to find the explicit solution to this recursion model. Be very careful. This recursion model is not in the form u sub t plus 1 equals a u sub t plus b. We need to first rewrite it in this form before we can use the formula. Okay. So the t plus 1 term, that has to be on the left-hand side. So let's rearrange. So 2p sub t plus 1 is on the left. I'm going to move everything else to the right. So this negative 4p sub t plus 3, this is going to go to the right-hand side. So that becomes positive 4p sub t minus 3. And then one last step, divide both sides by 2. So I'm going to divide everything by 2. So we get p sub t plus 1 equals 2p sub t minus 3 halves. And now we're in business. Now we can use the formula because it's in the form something t plus 1 equals your a p sub t plus your b. Notice that b is negative here. So I'm going to let you guys try this out. Go ahead, put it in the formula, or if you really like steps, use your steps. But I would recommend just using the formula and come up with the explicit solution. Okay, I'll give you guys a minute or two to give that a try. When you're done, when you have the explicit form, if you don't mind just raising your hand, just so I know how many of you are ready to take it up. Yes, this session is scheduled to end at 7:30. I might go like a couple minutes over depending on where I leave off, but it will be recorded. So if you do have to go, I totally get it. I won't be offended. We'll send you the recording via email. Okay. For those of you who are done, if you want to challenge yourself, try the next question on your own, go for it. Okay, I'm going to start taking it up. I know some of you are still trying it, and that's okay. You know what? This booklet is for you guys. So even if I take it up, write down the answer. And if you want to try it again after the session by yourself, go for it, right? Okay, so we have our A and our B and our P sub 0. So let's put it in the formula. Formula, that's our best friend. So P sub T, I'm just changing my U's into P's, equals the initial term, U sub 0, that is 5, minus B, be careful here, B is negative, okay? Divided by 1 minus A. So that's 1 minus our A, which is 2, times A to the power of T. So that's 2 to the power of T, plus B, which is negative, divided by 1 minus A, which is 2. And a lot of students that I work with before, most of the time with some practice, they're able to get to here. Where students get stuck is actually simplifying the numbers. By the way, in the past, calculators weren't allowed. I don't know about this year. I'm still waiting to hear confirmation, but let's assume it's not. Let's do some mental math here. When you have a fraction like this, you want to clean up the numerator and the denominator as much as possible. So let's clean up these denominators first. Ooh, sorry, someone confirmed. Thank you for letting me know. Confirmed, calculators are not allowed. Great, let's practice our mental math. So we have 5 in the denominator, 1 minus 2. That's negative 1. So essentially, I have a bunch of negatives, right? There's one negative there times a negative divided by a negative. When you have an odd number of negatives, it's negative. If it's even, then they group up in pairs and they become positives, but this stays as a negative. And then we have 3 halves divided by 1, which is just 3 halves. Anything divided by 1 is itself. Same thing over here. We have 2 negatives, so that makes it positive. So we have plus 3 halves. Let's keep going. 5 minus 3 halves. You need a common denominator, right? I'm going to multiply top and bottom by 2 to get that common denominator of 2. So we have 10 halves minus 3 halves times 2 to the power t plus 3 halves. And then finally, we simplify. 10 minus 3, that gives us the 7. 2 to the power t plus 3 halves. Sorry if I'm zipping through that a little bit, but some of the algebra stuff, I'll leave it for you to try out, okay? So that's the formula, and that is the explicit form, done. All right. Now let's go through a problem here, a word problem. We have an initial investment of $2,000. So great, that's initial. So I'm going to put U sub 0 right next to it. It increases in value by 50%. So now it's increasing, meaning our A has to be greater than 1, right? If it's increasing by 50%, meaning that the next year, I'm going to get my investment plus 50% on top of that. That's a really, really great return. So this becomes our A, which is 1.5. And then at the end of the year, the investor withdraws. Remember, withdrawal is your B, right? Takes away 500. So that's your B is negative 500. So part A, we want to create a recursion model for this investment. So we want to figure out the next year, the T plus first year. How much money am I going to have in this investment account? Well, that's going to be what's in there, the present year, what's currently in the bank account, but it's going to grow by 50%. So it's going to increase by 1.5 times. But then at the end of the year, I'm going to withdraw $500. So subtract 500. That's the recursion model. It's useless because if you wanted to find how much money there's going to be in year 10, you got to find how much there is in year 9, how much is there in year 8, and so on. So instead, we want to come up with the explicit solution. So it's formula time again. So let's put that in our formula. And sorry, guys, I'm going to zip through this a little bit in terms of the algebra. So U of t, U sub t equals U sub 0 minus b over 1 minus a to the t, plus b over 1 minus a. It looks hard, but you're just subbing in values, right? We know that a is 1.5, b is negative 500, and u sub 0 is 2,000. So let's put that all in. So we have 2,000 minus negative 500 divided by 1 minus 1.5 times 1.5 to the t plus negative 500 over 1 minus 1.5. Okay. I'm going to skip the algebra here and just give you guys the final answer. If you guys run into problems though, if you're like, I can't get your answer, please, please, please email me and I will help you through it, okay? But just to save us time, this is the answer once you simplify and crunch all those numbers up. Okay, let's answer part C and D here. Part C, how much money will the investment be worth in 12 years? So they're not giving us the amount of investment, so we're not going to replace U sub t. Oh, sorry, thank you. Sorry, someone pointed that out. It's 1,000 at the end there. My bad, just missed a 0. Thank you. Sorry, going back to C. How much money will the investment be worth in 12 years? That is in years, so that's a t value. So meaning we're going to substitute t with 12, okay? So we're looking for U sub 12. How much money is in the account in 12 years? Equals 1,000 times 1.5 to the 12 plus 1,000. And without a calculator, you can't really do much here. That's it. You'll leave it like this. I know on the quiz, you're required to put in a number. In that case, I guess you can use a calculator, but on the midterm exam, no calculator, so you'll leave it like that. Okay. All right, let's do number D together as well. So let's pretend the question changed. Instead of withdrawing $500, how much money would the investor have to withdraw so that the investment is worthless after exactly 10 years? So some students, this is a common mistake I've seen. They're like, okay, I did all that work in part B. I found this equation. Let's put t equals 10 and then solve for u sub t. Don't do that. This equation, we got that equation by assuming the investor withdrew $500 every year. But right now they're saying, no, B is no longer negative 500. They're asking for us to find the B value. So we're going to have to go back to our equation. This equation is going to become your best friend because you're going to use it so much. And what we're going to do is we want to solve for B. Okay? So let's go ahead and plug in everything we know. This is the amount of investment. We want this to be worthless. The number that corresponds to worthless investment is $0. So we want this to be a 0. The initial investment didn't change. The initial investment was, what was it? 2,000? Minus, we don't know what B is. So we're going to leave it as a B. A doesn't change. The rate is still, it's increasing by 50% every year. The t is no longer a variable because we know that it's going to be worthless in exactly 10 years. So t is going to be 10. Plus, we don't know what b is. We know that a is 1.5. So all of a sudden, we have this equation with just one variable that's missing, and that's b. Okay, and we have to solve for b. This is where the tediousness comes from. But like I said, when you're given an equation like this that's super messy looking, always start with your fraction. You want to simplify the top and bottom of your fraction as much as possible. See if you can rewrite it as something nicer. So the 1 minus 0.5 is going to give us our negative 0.5, right? 1 minus 1.5. So now we can simplify this. This is 2,000. We have two negatives. We have minus a negative, so that's a positive. And then we have b divided by 0.5. We don't really like decimals in fractions. Think 0.5 as a fraction. That's 1/2. Something divided by 1/2, something divided by 1 over 2, the trick is we flip and multiply, right? So it becomes b times 2 over 1, or 2 times b. Same thing over here. In this case, we have a positive and a negative, which makes a negative 2b. Oops, I have that power of 10 there. Okay. All right, continue. We want to solve for b. B is wrapped inside the set of brackets, so let's expand the brackets. So we have our 2,000 times our 1.5 to the power of 10 plus 2 times 1.5 to the power of 10b minus 2b. And now the b's are no longer wrapped inside brackets, they're outside of brackets, and we can solve for it by factoring. So a lot of little algebra steps here that I'm kind of flying by, I know, sorry. So now if I factor out the b, I get 2 times 1.5 to the 10 minus 2. That's just a number. I don't care how messy it looks, it's just a number. So I have some number here plus b times some number. To solve for b, I'm going to move everything to the other side. So we get a negative 2,000 times 1.5 to the 10 equals, I'm also going to divide both sides by this bracket that's in front of b. So it's divided by 2 times 1.5 to the 10 minus 2, and that is our b value. You're not allowed a calculator on the test, so this is what you will leave it as, okay? Someone's asking, if you didn't have the equation, so the formula, how would you solve this question? In a very difficult way. You would actually put in all the numbers, the information that you have, and whatever you don't have, you'll leave it as a variable, and you would use the steps that we've talked about. Please don't make me do it. Okay, you would use the steps, and then in the end, you would plug in t equals 10, and u sub t equals 0, and then you would have to solve for the missing variable b. Okay, copy it down, take a screenshot, whatever you need to, because we're going to move on. I know there's this question here. I'm going to leave this as an exercise for you. I'll make sure to send you guys the solution so you have them, but it's the same thing that we did before, okay? It's the exact same question, just changing the number, so I'll let you try that on your own, but I do want to dive into differential equations a little bit. If you do have to leave, feel free. We will email you the recording, but I want to at least get through some of the differential equation stuff so that next week we're not like super rushed. I can take a little bit more time to go through the new material, okay? So differential equations. Did they do DEs last year? Yes, they do DEs every year. They focus on it. It's a pretty big part of the marks where it came from. I'm assuming it would be for this year as well, okay? So first of all, what is a differential equation? I'm going to stop saying that. I'm just going to say DE from now on. It has the word equation in it, so it's an equation. This equation is special. It's not just y equals 2x plus 3 or anything like that. It's now going to involve some of its derivatives. So for example, the equation y prime, the first derivative, equals y plus 2 sine t. Or the third derivative, y triple prime minus 2y double prime minus x equals 2e to the y. So it involves y, it involves some of its derivatives, and it can involve the independent variable t or x or whatever it is, okay? That's a differential equation. The solution to a differential equation is the equation y equals something, where y equals something satisfies the DE. So it makes left side equals right side when I plug it in. For example, let's pretend that I know that y equals whatever. This is a solution. Then, well, it's a solution to, let's say, this example, the second one. Then what it means is if I take the third derivative minus 2 times the second derivative minus x, that will equal 2 times e to the y. That's a solution. And there's some definitions you need to know. And these are easy marks if you know these definitions. The order of a DE is the highest derivative in that DE. So for example, in these two examples here, this first one, if I look at my derivatives, there's only a first derivative. So this is order 1 or first order. So first order. If I look at my second equation, the highest derivative is my third derivative. So this is third order or order 3. That's it. That's the order of a DE. Now there's different types of differential equations out there. There's your linear versus nonlinear and your homogeneous versus inhomogeneous. So let's talk about linear versus nonlinear. Remember, linear is your y equals x, right? Where x just has a power of 1. There's no trig, there's no exponential, there's no log, it's just to the power of 1. So a linear DE is the same definition. If you look at your y or its derivatives, they all have power of 1. It's y prime, y double prime. Those are the derivatives. They're not the power, they're not the exponent, right? Even this guy, this is the nth derivative, not the nth power. So they all have power of 1. That's what makes it a linear DE. There could be stuff in front of your y's. That could be whatever it wants. I don't care. But the y's themselves are linear. So for example, if you look at this guy here, the y's and its derivatives are all linear. The t terms that are being multiplied by it, those don't have to be linear. Just the y parts have to be linear. And if the y parts are not linear, then it's a nonlinear DE. For example, this guy down here, if I highlight all my y's and derivatives, notice that this guy has a power of 2. This guy is a reciprocal. This guy is wrapped inside a trig. So none of these are linear. As long as you have one term that's nonlinear, the whole thing is nonlinear. Okay. Homogeneous versus non-homogeneous. These are also two types. These ones are easy to spot. The part that doesn't have any y's, we always write them on the right-hand side of the equation. If there's nothing there, if it's 0, then it's homogeneous. If it's non-zero, it's inhomogeneous. Sorry, there's a typo there. There should be a 0 there. So if you look at this example here, all these terms that have y's are on the left. All the other terms are on the right, which is just a 0, so it's homogeneous. The second example, you might think, okay, Jess, there is a 0. Why is this inhomogeneous? Well, if you highlight all the terms with a y, there's this term, this -5, that doesn't have a y. So we need to pop him over to the other side. And the instant we pop him over, it's no longer going to be 0. So that's why it's inhomogeneous. Okay. Let's do this. Let's just cover this this page. There's only like 2 more questions on this page, and then we'll call it a day, and we'll cover everything else next time. Okay. So we want to fill in this table with the order of the DE, whether it's linear, nonlinear, and whether it's homogeneous or not. So my trick for you is grab a highlighter and highlight anything to do with the dependent variable. So if you look at these questions, they're all U of t versus y's. They're u's, not y's. If they're y's, you can highlight the y's, but here we're going to highlight anything to do with u's. So in this first one, the order, I'm looking for the highest derivative. The highest derivative is this one, second derivative. So the order is 2. Is it linear or nonlinear? Well, look at the u prime, u double prime. They're both power 1. They both have an exponent of 1. So it's linear. Is it homogeneous or inhomogeneous? Well, there's this guy that I haven't highlighted, so I would have to toss it over to the right-hand side, which would make it non-zero. So since it's non-zero, it's inhomogeneous. Okay? So why don't you guys take 2 minutes, fill out this table, just like 2 minutes real quick, and then we'll take it up, and we're almost done. Sorry, I'm going a little over, guys. I just really didn't want to brush over anything when there's questions, so. Okay, hopefully you were at least able to try the first couple ones. If you didn't get all the way to the bottom, that's okay. I'm going to give you the answer so that you can try it again on your own. But I want to get you guys out of here at a reasonable time, okay? Okay, and we will get to solving DEs next time, okay? So sorry I didn't mean to do it today, but we're going to do it next time. My bad. Okay, looking at this first one, I've already highlighted everything to do with the U's. Remember, anything to do with the U's should technically be on the left-hand side. So imagine we've moved that U triple prime term to the right. Okay, so we subtracted it, or to the left, my bad. So the order of the DE, the highest derivative is this third derivative. So the order is 3. This one, I have a product of U and U prime. So this one's non-linear. Remember, for linear, they have to be by themselves to the exponent of 1. They could be multiplied by t's or x's, but no dependent variable. So here, they're being multiplied, so it's nonlinear. This one, if I move this term that has a u over to the left, I will have a 0 on the right. So this one is homogeneous. Okay. This next one, highest derivative is 2. But be careful. This big bracket raised to the power of 3 means that our exponent of the second derivative is 3. So this one is non-linear. And if you look at the terms that I didn't highlight, oh, there are some terms left over. And some people would say, okay, this is inhomogeneous because there's terms. But be careful, there are ones on both sides. So technically I can just subtract 1 from both sides and they'll disappear. They cancel each other out. So we actually end up with a 0 on the right-hand side. So this one actually is homogeneous. Okay. And then for this next one, the highest order, whenever you have a bracket with the number like that, it doesn't mean an exponent. That means the derivative. Okay. So this is a derivative. So the highest order derivative is actually order 4. Each one is raised to the exponent of 1, each u term. So this one's linear, and it's non-homogeneous because there's a bunch of other stuff left over. So non-homogeneous. Okay. And then our last one here, the highest derivative is 1, so order 1. And this one is linear because they're both raised to the exponent of 1. I don't care what t terms they're multiplied by, that's fine. This one's still linear. And there's no other term, so it's homogeneous. Okay, let's call it there. I don't want to go too much over it. Let's call it here. If you have questions, stay behind. And like I said, if you didn't fill out the survey, please fill it out so that we know what's the best time for you guys. We will open up registration for the rest of the weekly starting tomorrow. If you have feedback, please let me know. We'll continue on the rest of DE next week. I'll make sure I cover all of it, okay? All right, answering questions now. So doesn't homogeneous and inhomogeneous only apply to linear DEs? No, it actually can apply to different equations, but you're right. A lot of times your prof will ask you just on linear DEs, but they can give you non-linear DEs and ask you if they're homogeneous or not as well. Okay, why is the second one non-linear? Okay, yeah. Yeah, this one. I'm gonna erase some stuff and actually rearrange it so we see it more clearly. So if I rearrange it, moving this term over, I get u t times u prime t minus the third derivative divided by sine t equals 0. So it does equal 0, so it is homogeneous. But it's non-linear because think of your variables. We no longer just have y as our dependent variable. Our dependent variables are y plus all of its derivatives. So in this case, u and all of the derivatives. So I have 2 dependent variables, which are u and u prime, multiplied together. That's why it's non-linear. Okay, for it to be linear, it has to be very specific. It's some kind of t term times u, plus some kind of t terms times u prime, plus some kind of t terms times u double prime, and so on. That's the only way it's going to be linear. But since I have a u times a u prime, that's why it's non-linear. Okay, let me know if that makes sense. If there's no derivatives, what would the order be? Good question. If there's no derivative, then the order is 0. It's no longer a differential equation. It's just a regular equation, right? If my equation just has y and x's, but there's no y primes, then it's just a regular equation, right? Yeah, no problem. If you have feedback for me, let me know. I'm happy to improve to make this even better for you guys. Why is the last example linear if u prime is not by itself? Good question. Okay, let's go down here. So this last one, right? So again, for it to be linear, I can have whatever t terms I want. I don't care how messy it is, times a u, plus whatever t terms I want times a u prime, plus whatever t terms I want times a u double prime, and so on. So here I have this t term, but notice that it only involves t, so it can be as messy as it wants, and then times u prime. So that's why it's linear. Okay, let me know if that makes sense. I know these ones can be tricky. Okay, and that's all I have for you guys. So thanks for joining me today. Sorry it went a little over, but if you guys have more questions, let me know.